Right here. See? The proof for the equation of a derivative, right? Once we apply a derivative.
No, that's only the derivative for x to the power n.
Yeah, this is the concept of a derivative.
Mm.
They derive it like the main concept of the derivative, just like a plane derivative, taking it. They derive it as you have already taken the limit.
Yes, they have to. The application of limit in a derivative, that's the main thing. Okay? Can you explain to me this thing that you just read? Did you understand it?
Yeah.
Okay, what is it saying?
Okay, so, well, first of all, up here, it's where specified that some values, some equations where a small change in x may produce a larger change in f of x. We say that the f of x is relatively sensitive to changes in the x.
Okay.
And in the question itself, which is after that, genetic data and sensitivity to change, basically said a monk working with garden peas, his careful records show that if p, a number between 0 and 1, okay, is the frequency of the gene for smooth-skinned peas, which are dominant, and 1 minus p is the frequency of the gene for wrinkled skinned peas, then the proportion of smooth-skinned peas in the next generation will be, and it gives an equation which turns out to be y is equal to 2p minus p squared.
Okay.
And next it goes on to just explain that the smaller values of, like the early values of p, the smaller values, right? They give you a higher increase, like more sensitive change. But once you get to a larger value of p, the change kind of becomes lower. It's no longer sensitive. And they basically prove that by taking the derivative of the graph and showing that when p is 0, then the change of y, which is basically the proportion of smooth-skinned peas in the next generation per p, that is much higher when it's a smaller value. And then like 0, the value is 2, but once it goes to 2, the value becomes 0, and when it goes to 1, the value becomes 0.
Okay, so that shows on the graph. Basically,
essentially it's saying that whenever there's a smaller value of p, it's more sensitive, but for a higher value of p, it's less sensitive.
Okay, but the question now is, where is the application of limits in here?
Application of limits? They took the limit of the graph. They took they took the derivative of the...
Yeah, okay, but the other question is also, why did they take derivatives? What did you understand?
What I understood, they just took the derivative to prove their point.
Yes, but why would derivative help them to take their prove their point?
The graph itself is the proportion of smooth-skinned peas.
Okay.
For the next generation. So when you take per unit of p, you take that per unit of p.
Unit of p meaning, what does the unit of p mean?
Okay. P, a number between 0 and 1, is the frequency of the gene for smooth-skinned peas. So how frequent they are.
How frequent the gene is gonna come in the next generation.
Yes.
Right? So for every unit change of that frequency,
yes,
what are they trying to see?
They're trying to see the proportion of smooth-skinned peas in the next generation.
Right. So there might be, you can have a bunch of increase in unit change.
Yeah.
But within the total proportion, the actual expression of the gene could be a little different than that. It might not be straightforward, right? As you said, if it increases a lot, then actually the proportion becomes slower. So why take a derivative? What is the derivative doing in here? The derivative is
that is the derivative
for every unit change. No, but originally there wasn't a derivative.
Yes, originally that equation was basically giving you the proportion of smooth skin P's in the next generation.
Yes.
Once we take the derivative.
So let's say there are 100 P's.
Yes.
This is how you explain things, okay? So there was 100 P's.
Yes.
In the next generation, we would expect that out of the 100 P's, let's say 30 P's would have smooth skin.
Yes.
Right? Okay. So that's what the original equation is.
Mm-hmm.
Now, taking a derivative
of they'd be dominant, so wouldn't it be more like maybe 70?
Okay, yeah, so we're talking about dominant. Okay, so 70 smooth skin.
Okay.
That's the proportion.
Mm-hmm.
But why take a derivative? What are we doing?
We're taking a per unit of P, which is how likely there's going to be a smooth skin P.
Taking the unit.
So it's okay. Once we take the derivative of this equation, we basically get how many, like the proportion of smooth skin P's in the next generation, right?
Yes.
Dependent to the frequency
mm-hmm.
of how many P's, how many smooth skin P's usually occur.
Really?
Frequency of gene for smooth skin.
Gene is the important point.
Gene for smooth skin.
This is a genetic problem.
Mm-hmm.
And we're only talking about how frequently a certain gene is coming.
Yes, occurring, yeah.
That will determine
the proportion.
What does the gene do basically? The gene is inside the cell, and what you're seeing outside is the phenotype.
Yes.
Genotype, phenotype, right? So the phenotype is smooth skinned seed. Genotype is the gene.
Yes.
If we can figure out the change per unit
of each increasing
genes,
yes,
then we can probably figure out the rate at which the proportion of the frequency,
the proportion of the next generation of
smooth skin
yes.
frequency would be changing, right? So that's what they're trying to figure out. And initially they saw that if you have a larger frequency of genes, then the proportion of smooth skin declines or becomes slower. But if you take the unit change, you can actually figure out the rate. And this rate later on became a straight line.
Oh yeah.
Right?
It became, yeah.
It did become a straight line, which means what now? The probability of the frequency of the gene was 0 to 1.
Yes.
That's the range where it was moving. Now, as they moved away from 0, what happened? So if it was increasing, it would look like this.
Oh yeah.
If it was decreasing, it looks like now this.
Yes.
Right? So as the frequency of genes increased, it actually decreased.
Yes.
In a linear fashion. They found it only when they saw it through calculus. They could have seen it in here, but they couldn't find the rate in there. In the original equation, they didn't have an idea of the rate of change. You see? But here they actually had the idea of the rate of change of the change, the frequency change of this smooth skin. They knew it was declining because at first it went high, then it went like this. Okay? But they didn't really know exact rate of change in there to find that. So this is basically a fundamental use of calculus again, just to find the rate of change of some output or outcome. Right?
Yes.
So application in genetics. Previously, application in marginal cost. All using the same concept. The rate of change per unit change in the independent variable to make a change in the dependent variable. Got it? Okay.